In this video, we're still talking about types of reaction rates, but we want to talk about one specific one, and that's known as differential rate law. So we've already talked about instantaneous and relative rates. Now those questions can be asked, but they're not as frequent as this particular one, differential rate law. And what I call this one is the table logic approach. So table logic. So if you ever hear me say, hey, you got to use table logic or whatnot, this is what I'm referring to, differential rate law, or sometimes you'll see me abbreviate it as DRL, differential rate law. Now, the type of data that you have for differential rate law is very specific. If you see down here at the bottom of your page, you have initial rate, you have several different experiments, initial rate, initial concentration of one reactant, and initial concentration of another reactant. So the type of data that's given is rate versus concentration data. And that's very important to pay attention to, because when we get to the next type of reaction rates and how to figure out that, then there's different type of data that can be given. So the data for differential rate law is rate versus concentration. Now, the rate law expression, what this is, and remember an expression means that I'm just putting in variables. I don't really put in numbers. We are going to write that as rate equals lowercase k, and I like to do it in the cursive K. If you put a big K, then that would be wrong, because big K stands for equilibrium constant. This little k stands for something called rate constant, which we're going to talk about next. So rate equals K. You plug in the concentration of your first reactant, A, and you raise it to something called the order. What an order is it's a number that shows the relationship between a concentration change and how it affects the rate. We're going to talk about those in just a second as well. Then you put in concentration of B and you raise it to its order as well. So if I'm writing a rate law expression, the only numbers that need to be plugged in is the order here and the order here. You do not want to plug a number in for rate. You do not want to plug in a number for K. A is whatever the reactant is. I don't plug in any numbers. I just write whatever that reactant is. I write in B, whatever that reactant is. But the numbers that I do plug in are the orders. Now the orders are going to be 0, first, or second. So for this here, you're only going to plug in a 0, a 1, or a 2. Now I know this all sounds really confusing now, but I promise it's going to come all together. So this is called rate law expression. Rate constant K, what this little thing there is, it depends on the type of reactants that you have and what orders they are. Now, how you find this rate constant is you will have one of these experiments. So let's say I look at this data table down here, and I plug in all of my information. So I plug in my rate, I plug in my concentration of A, and beforehand, I have to figure out what the order is. So that will either be a 0, 1, or 2. I plug in B's concentration, and I plug in whatever order I found it to be. And I just solve for K algebraically. Now, K has units that change. So rate is molarity over whichever time unit you have dealing with. A is concentration, so that's molarity. Now, if this is an order of 2, then this is going to be molarity squared. If this is B and it's a molarity of, or an order of 1, then it's going to be molarity to the first. Now, to solve for K, do you see how I'm going to be dividing by those molarities, dividing by this molarity? So what's going to happen is one of these molarities is going to be eliminated. And this is always what happens for K. One of these molarities that you see is going to be eliminated. So my units for K, in this case, K's units would be 1 over molarity to the second times whatever time you're working with. the units of K change? It depends on the overall order, which you see that down here, overall order. What the overall order is the sum of these orders. So my overall order for this particular one would be 2 plus 1, which is 3. And because there's molarity to the third here, and because there's a molarity over here on the other side of the equal sign, I'm always going to eliminate one of those molarities. So one way you can look at the units for K is by taking 1 over molarity raised to the overall order minus 1. I raise it to that power, and then I plug in whatever time unit that I have. So let's do another quick practice problem with that. I'm going to select all of this and delete, and then go back. So let's say I have this as my rate law expression. I have rate equals K. Remember, I'm not plugging in numbers. Let's say I have A to the second order, and I have B to the second order as well. What would my units be for K? Well, what is my overall order? I have molarity to the second as well. So that's overall molarity to the fourth. Here, I have molarity over time. Now to solve for K, I'm going to have to divide by that, right? So that basically eliminates one of these molarities, so that makes it molarity to the third. And I have to divide that over, so it's going to be, K is going to be some number over molarity to the third times whatever time unit you're working with. So that is how we find the units of K, and you're going to get lots of practice with this whenever we're working practice problems. Here's another thing you need to know about K. So step 1, how do we find it? We just use algebra. We plug in rate, we plug in concentration, we plug in concentrations. We need to know those orders beforehand, and we just use algebra to solve for K. Step 2, how do we find the units for K? Well, we use the overall order, and we eliminate one of those. And it's some number over your molarity raised to the overall order minus 1, because we're eliminating 1, right? Times your time unit. So what would I find for my time unit? I would have to look at my data table. So this one, in this case, if I was looking at this experiment below, my time unit would be in hours. So be careful of that. Step 3, something else that you need to know about K. K is a constant unless you are dealing with a temperature change. So K is temperature dependent. If you change your temperature, but I still have A and B that are 2 and 2 order here, my K will change. And we're going to talk about that. That has something to do with activation energy later on. So those are the things that we need to know about K. Now, that leads us into a very important question. Okay, Kelly, I know that I gotta figure out K from this. I know K has different units. I know I need to know the orders of these, but how the heck do I find that? What do these orders mean? What your orders mean is the relationship between a concentration change and how that affects rate. So we have to figure out that relationship. That relationship is going to be that number. So what I want to do is look at this real quick and figure out what is zero order, what is first order, what is second order, what does that mean? So zero order, what that means is that a change in concentration has no effect on rate. So I could double my concentration, and guess what? My concentration will not change. So no change. I'm sorry, my rate will not change. I think I said concentration. If I double my concentration, my rate will not change at all. Even if I triple my concentration, my rate will not change at all. Now, how do we represent this mathematically? Why is it zero order? Why do we give it that number? Well, what is 2 raised to the 0? It's equal to 1. What is 3 raised to the 0? It's equal to 1. And if my rate doesn't change, isn't it like saying that it's times 1? It's the same number, right? So that's where we're getting this zero order. We have our concentration change is raised to the zero order, which means our rate does not change at all. So this is our mathematical relationship and where zero order comes into play. Now let's relate that to first order. I'm going to have to delete some space here. So first order, what does that mean? Well, first order means that my concentration change is proportional, that's what the little fishy symbol means, to my rate change. My concentration change is proportional to my change in rate. So, let's say I were to double my concentration. What would that do to my rate? Well, that would also double my rate. What if I tripled my concentration? What would that do to my rate? Well, that would triple my rate as well. And you guys get the idea. Well, how does this make sense mathematically? Why is it known as first order? Well, if I take my concentration change, which is 2, and I take my rate change, which is 2, what would this exponent be? Well, that exponent would be 1, because 2 raised to the first order, or raised to the first power, is equal to 2. Let's do the same thing with 3. 3 raised to what power is equal to 3? Well, that answer over there would be 1. So what an order is it's the relationship between your concentration change and your rate change. Now let's look at second order. Let me select all, let me delete again, and we will go back to second order. So second order. What's happening here is if I change my concentration, then it causes my rate to change by that number squared. Now that's a mouthful. What does that mean? So this is that number. Well, if I double my concentration, what that is going to do to my rate is cause it to be 4 times the rate. If I triple my concentration, then it's going to cause my rate to be 9 times that rate because it's this number squared. So 3 squared is equal to 9. 2 squared is equal to 4. Well, what if I even quadruple? What would that do? What's 4 squared? That's 16. So I have 16 times the rate there. How does this represent second order mathematically? Well, 2 raised to the second power, indicating second order, is equal to 4. 3 raised to the second power, indicating second order, is equal to 9. And you guys get the idea. 4 raised to the second power, indicating second order, is equal to 16. So all these orders are doing are showing the relationship between a concentration change and how it affects rate. Because remember at the very beginning, we talked about what are some factors and how does it affect rate? Well, concentration is one of those. If I double my concentration, then I'm going to have 4 times the rate. That reaction is going to happen even faster. So this is for us to mathematically put a quantitative portion to those factors that affect our reaction rates. Now, let's figure out how do we apply this knowledge? We know our orders now. We know what the relationships are. How do we use this in an example? Now, one thing that I want to know, very important to know, when you're working with rates and trying to figure out the rate of a reaction, step 1, you have to do it experimentally. Okay? You cannot figure out the rate of a reaction without conducting an experiment. Secondly, all orders do not have to be 0, 1, or 2. Okay? So all orders You do have to find them experimentally, but they can be fractions, they can be anything other than 0, 1, or 2, but 0, 1, and 2 is what we're going to be working with AP because those are the most common. So just notice that orders do not have to be those numbers. That's just the most frequent that we'll see there. Okay, so they can be other things. Let me see if there's anything else I need to add before we move along. I think that's it. Okay, so now let's refer to this experiment. So I'm going to select all, delete again, and let's scroll down. So what we have in this example is a couple of different experiments. So like I said, whenever I'm figuring out rates of things, I have to figure it out experimentally. If I don't conduct an experiment, I can't figure out my rate. So what I'm looking at is 5 different experiments. And what I've done is changed my concentration of A throughout that whole thing. And I've also changed my concentration of B. And therefore, I've gotten my rates out as my data. So there are a couple of things that will be asked here. We might have to figure out, step 1, the order with respect of A, or with respect to A, and with respect to B. I might want to change this to T-O, to B. Now, this term here, order with respect to A, and order with respect to B. All that is a fancy term for is, hey, what's A's order? What's B's order? So that's what that means in case you come across that and you get a little confused. So we want to figure out the order of A and B. Another thing that we want to be able to do is figure out the rate law expression. And the last thing we want to do is figure out what is the value of K with the proper units. Now, so like I said, we have to figure out what the units are of K depending on that overall order. So let's figure out how we do this. All right. If I want to know my order of A, I have to figure out 2 experiments in which A changes concentration, but B stays the same. So let me repeat that, very important. If I want to find the concentration of A, I need to hold B's concentration constant. The reason why is because, well, if I have A changing and B changing, I don't know really which one is affecting the rate. So whoever is changing concentration, that is the one I'm figuring out how that affects rate. I want to keep the other one constant. So I have to pick an experiment that I have to compare between. So I'm basically picking 2 experiments. Both of them should have concentration of B staying the same, but should have concentration of A changing. And we're going to see how that concentration change affects my rate. So if I want to figure out the order of A, I might want to pick 1 and 2 because I see that A is changing concentration, but B's not. Or I could pick 1 and 3 because B is staying the same. Or I could pick 2 and 3. Which one you pick doesn't matter as long as B is staying the same if I want to find the order of A. So let's just, since these 2 numbers are close together, let's just pick experiment 1 and 2. So you ask yourself, what is happening? What is this concentration changing by from experiment 1 to 2? Well, my concentration of A is changing by 1.5 times. Does that make sense? If you can't do that math in your head, all I would say is 0.75 divided by 0.5, and you would get the answer 1.5. Now, what's happening to my rate? Well, my rate is not changing at all. So if my rate's not changing, then that means it's just 1 times. So then you ask yourself, well, what order would cause that to happen? 1.5 raised to what order equals 1? You see how I'm looking at not these numbers, but I'm looking at what's jumping, what's changing between my concentration and my rate. Well, 1.5 raised to the 0 order, raised to the 0 will equal 1. So what that means is that A is 0 order. The order with respect to A is 0. Now, how would I justify this on a free response question? Well, one thing that you can do is you can say, well, with B held constant, my concentration of A in experiment 1 to 2 increases by 1.5 times, which causes my rate to not change. Therefore, my order with respect to A is 0 order. So you see what I'm doing is I'm putting this stuff in words. You can't just say this right here, that's my answer. Okay? I have to say I'm holding B constant. I'm using experiment 1 and 2. This is what's happening to this concentration. This is what's happening to my rate. Therefore, it is whatever order. So that is the foundation that you need to put, and you can fill in the blanks from there. So again, this is staying constant. I'm using experiment blah and blah. My concentration is doing this, which is causing my rate to do this. Therefore, it is that order. Okay, so that's a good way to justify and get all of your points. Now let's look at B. Let's figure out what the order of B is. Now, same thing. If I want to figure out the concentration of B, I have to hold concentration of A constant. It cannot change. So I might want to choose either experiment 1 and 4 or experiment 4 and 5. Which one you choose doesn't matter as long as A is staying the same and B is changing. So I want to just use experiment 1 and 4. So you see how A is constant there. Let's figure out what's happening to B's concentration. B is going from 0.2 to 0.4. So you see how B, my concentration is doubling from 0.2 to 0.4. My A is staying the same. And let's see what is happening to my rate. So that 2 times in concentration is causing my rate to double. It's going from 0.005 to 0.01. So that 2 times in concentration is causing my rate to double as well. Now, what relationship gives me 2 raised to what power is equal to 2? Well, the answer there is 1. So what that means is that B is a first order reaction. So the order with respect to B is 1. Now I keep that same format if I'm explaining it in free response. I would say, well, I choose experiment 1 and 4, which caused my concentration of A to stay the same. My concentration of B doubled, which caused my rate to double as well. Therefore, it is a first order reactant. And that's all you have to put. Now the next thing that we want, now that we know our orders, we have to figure out what is our rate law expression. So remember, the only numbers that we plug in for the rate law expression are the orders. So I'm going to say rate equals K. Make sure it's a lowercase k because that means rate constant. A to the 0 order times B raised to the first order. Now, you could also write it like this. A to the 0 order, that's essentially just 1, right? So I could write this rate law expression, rate equals K, B and it's understood to the first order. So either one of these two are acceptable. Now let's answer the last question. What is the value of k with its units? So, how we figure out k's numerical value is we just take any of these experiments and we plug them into our rate law expression. Once we do that, we then can just algebraically solve for k. How we find the units of k, we can either do it by eliminating my units algebraically, or you can remember to take the overall order and subtract 1. So the overall order here would be 1, because it's 0 plus 1 is equal to 1. So if I want to find the units for k, I'm going to write this up here. It would be 1 over m, overall order is 1 minus 1 is equal to the 0, times whatever time you're working with. Now, where I look at time is figuring out what time is used in my experiment. So right there, I see hours. So I'm going to plug in hours. So this is one way to express my units. Now, not only do you want to figure out units for k, but you also want to figure out the numeric value. So let's just say that we choose experiment 1. We want to plug that information in. So I'm going to use a different color. Let's use blue. And let's plug in the values for experiment 1. So rate is 0.005. K is what we're solving for. Let's put those units down too so you can see how they cross out. So that's molarity over hour equals K. That is concentration of A to the 0, which is just nothing. So let's just use this one, B raised to the first order. So B's concentration is 0.2 molarity raised to the first. Now, what I'm going to do here is divide by 0.2 m on both sides. 0.2 m on both sides. And this is like saying molarity over 1. So you see how I have molarity here. I know you guys don't do skin over guts, but skin over guts is where I take the outer portion and the inner portion. So I have molarity over molarity times hour. So you see how those two molarities actually cancel out. So that's why we're left with 1 over molarity to the 0 times hour, or that's just 1 over hour for my units there. And I promise the more you do this, the more it will make sense. Basically what's happening here, boom, boom, those units are crossed out, okay? So 0.005 divided by 0.2, we would figure out that value, and that value would be equal to your K, your rate constant. Once you figure out that numerical value, you then put it over your units. So over hours would be what it is for this case. You can leave the m to the 0 in there as well if you like. Just anything raised to 0 is equal to 1. So you can leave it out if you need to. So I know this was a lot thrown at you. This is how you do differential rate law. It's table logic. So what I have to do is figure out the orders from the experimental data. The orders, all of this must be found experimentally. Then you can write your rate law expression from there, and then you can figure out the value of K and make sure you figure out those units accordingly. So I hope this helped you a little bit. We are going to do lots and lots of practice with this, so don't fret if you don't get it right off the bat. I promise it's easy after you get a few under your belt. So I'll see you in class.